if we're looking at flow of a continuous fluid, we often wind up neglecting the gravity terms. Now, when can we get away with that? Well, let's look and see if we can rearrange these equations. If we have g of x equal to negative g di h di x, that just deals with the fact that h goes upwards if we've got x and y on a slant going downwards. If h decreases as x increases, then that'll give us a component of gravity acting in the x direction equal to negative g of x di h di x. We can rearrange our Navier-Stokes equations to still have the acceleration term, and then have a term here that's a combination of the pressure term and the gravity term. And this is just by substituting g of x equal to negative g di h di x into the equation and combining the two terms. And we've got the same viscous term. So this is the force per unit mass due to both pressure and elevation change in the x direction. It's positive in the x direction if the pressure drops with x. So if we're going from a high pressure to a low pressure, that'll push the fluid in this direction. Or if we're going downhill, if h is dropping with x, if di h di x is negative. Or obviously if we have both, a pressure pushing this way and gravity pushing that way, that's going to give us a positive force in the x direction. So we can push with a pressure difference, or we can push with an elevation difference. The equation looks exactly the same, so we get exactly the same effect. If we solve the Navier-Stokes equations with gravity neglected for, say, a flow over a sphere like this, some of the flow goes over the top, some of the flow goes under the bottom. We're neglecting gravity, so we don't see any difference from the top to the bottom. It'll be symmetric between those two, and we'll get that the pressure on top is equal to the pressure on the bottom. That's if we completely neglect gravity. The solution would be the same if we put gravity in there, except the pressure on top plus rho gh on top would be equal to the pressure on the bottom plus rho gh on the bottom. So all that neglecting gravity does is, when we do our solution, we wind up with no difference in hydrostatic pressure. If we were at a higher elevation here and a lower elevation there through a continuous fluid and nothing was moving, the pressure on the bottom would be higher than the pressure on the top by the difference in height and the density of the fluid. So we won't see the hydrostatic pressure if we ignore gravity, but the rest of the flow doesn't change at all, and that makes our lives simpler.